So hello guys, welcome to the second day of IRDC, and the first team which we have today is Team Aurora from PSG. So have they joined? Yeah, so guys, all are here.
Yeah, hello, sir. Good evening, everyone. I am Subramanian. I am the current team captain of Team Aurora, and we are very happy that we have participated and we come to these finals. We are ready with our presentation. So, shall we start our presentation, sir?
Yeah, you can start, and just before you start, let me remind you the guidelines. So you will have 15 minutes.
So let me
and
share my screen.
4 of you can speak during the presentation, and after that, all of 10 of you can take part in the Q&A session. And
Sure.
if you exceed the time of 15 or 16 minutes, we will stop you there. So just keep in mind to complete the presentation within this time.
Sure, sir.
Yeah, you can share presentation now.
Let me share my screen first. So the hosts have disabled the participant sharing the screen, sir.
Okay, we'll enable that. Can you share it now?
Let me check, sir. I guess no. So it's still disabled, sir.
Just a second. Just a second. Yeah, now you can share.
Yeah, 1 second, sir.
Hello. Good evening, sir. Is my voice audible to everyone?
Yeah, you're audible.
Sir. Okay, sir. So let's start our presentation. So good evening, everyone. This is Haravind, the current vice captain of PSG Team Aurora, and we are very proud to present our IRDC report. So let us first introduce ourselves. Our team, PhD team Aurora, consists of 42 undergraduate students. We are divided into 5 subsystems, mainly mechanical, electrical, space research, operations, and logistics. Mechanical involved in the fabrication of chassis, suspension, and robotic arm, whereas electrical subsystem looks into the power system, drive system, operations and controls, communication and ROS. Whereas the space subsystem, space research, or the science task focuses on proving the life sources using ML, DL, sensors, and instruments, etc. Operations under the operations subsystem, we will be seeing into the social media and other handlings. Logistics and finances looks into the money and financial issues. So first subsystem. Now let me explain about the space research subsystem. So usually the space research subsystem focuses on providing evidences of past or future or present life on Mars. So we will be doing various analysis initially in order to prove this. So analysis number 1 is the atmospheric analysis. For analyzing the atmosphere of Mars is usually crucial because when we know about the properties or the characteristics of the climatic conditions on Mars, it will be very useful. So we will be using atmospheric sensors. So the sensors involved in atmospheric in this sector are gas sensors, pressure, humidity, dust sensors, and we are also kept a Martian microphone in order to record and hear the Martian sounds on board. Next. So coming to the soil sensors. The soil sensors focuses on planting the sensor into the soil in order to determine various factors like the ground temperature, which will be crucial in determining the temperature difference between the atmosphere and the ground. The enzymatic sensor plays an important role in providing the evidences of biomolecules, whereas the moisture sensor does its work of finding any moisture, and the conductivity and pH sensor determines the pH, which is very useful in determining the nature of the soil. Next is the spectrometry. The instrumentations which we have used on board includes various types of cameras and spectrometers. So initially coming to the spectrometers, we have gone to 3 types of spectrometers. That is namely the deep UV resonance Raman fluorescence spectroscopy, which focuses on determining the organic molecules and potential biosignatures. Whereas the ground penetrating radars does its functions by determining the subsurface, underground imaging, and analyzing. For example, it can also help us in determining the underground plates shape and their angles, how they are placed. The miniature thermal emission spectrometer plays an important role in determining the thermal inertia, which is an important factor to be considered on Mars. The night vision hyperspectral arm camera is used to determine the fossil and mineral detection using the deep learning algorithms and techniques. Next is the meteorite and sample set detection. This is a completely ML and DL based algorithm which we have prepared in order to determine the origin of the meteorite. We will be analyzing with our cameras on board, determines from the meteorite composition, and it determines the point of origin. Whereas the sample set detection is determined using the same cameras, which plays an important role in giving us the in giving us a point where we have to sample and collect it. Drill system. Our Rover's drill system usually works on the principle of ultrasonic rotary percussive drilling technology. It's driven low power, so it is very useful. The frequency is around 20 kilohertz. It has a sub-harmonic acoustic component in order to reduce noise. The drill diameter is 8 mm, and the depth it can drill is 150 mm. Drill bots. Drill bots is a new concept which we have done this year in order to determine and know about the subsurface parameters. So we will be deploying this drill bot. It gets discharged from our rover and it goes underground in order to collect samples and to deep dive into the subsurface. So it has 3 parts. It is made up of aluminum 3004 alloy. It's communicated using the RF transceivers. It has DC motors, which is 12 volts. It is powered by lithium battery. The IME sensors provides the body orientation and its forces. Next, coming to this mechanical subsystem. The mechanical subsystem, let's see into the first chassis. The chassis, the material of the chassis which we have developed is aluminum 6063 T6. Moreover, it is of hollow circular pipe cross section which we are used to build and fabricate. The resilient truss structure helps us in giving a better durability. The overall rover is welded using the TIG welding methodology, and micro shielding is done for isolation and protection from radiation. Next is the suspension system. The suspension which we have got is a spider wider structure, rocker body, which is an independent type of suspension, which works like it has two wheels at the front and the back, and four at the left, two at right and two at left. Moreover, front wheel has a wheel actuator for traction. It is also made up of circular cross-section hollow member. The wheels is usually the honeycomb structure with the threads, and the material is copper, aluminium, manganese alloy, which is used to travel on the polar regions, which is covered usually by ice. Next is a robotic arm. The robotic arm is 6 degrees of freedom. It can reach a maximum height of 1 meter, whereas the material is made up of alpha titanium alloy. Each link has a separate actuator, which is done by servo motors. The robotic arm consists of grippers, cameras, sensors, and then the drill system, etc. Lubricants, fasteners, and paints. This time we have used the lubricant Maxine 4059 and graphene in order to reduce the friction. The paint, we have painted our rover in the color of gold in order to protect it from various things. Moreover, we have used C300 collision resistant stainless steel fasteners throughout the fabrication of the rover. So now electrical subsystem will be explained by Arifa.
Yeah, am I audible? Hello.
Yes, you are.
Yeah, electrical subsystem, it consists of the following subsystems. The power system will be explained now. Okay, the power system mainly consists of RTG and battery. RTG is like a radioisotope thermoelectric generator, which is a nuclear battery which consists of radioactive substances, primarily plutonium, which converts radiation heat into electricity. It is converted using Seebeck effect by employing thermocouples. Okay, during peak hours, battery will be used. Like the battery which you are using is lithium iron phosphate. The battery cell voltage is individual cell voltage is measured about 3.2 voltage, and its overall capacity is about 5,000 milliampere hour. Okay, when lithium diethylchloride is used as auxiliary battery, which backs up the main battery. It primarily used for supplying communication and navigation. Like when a rover is stuck somewhere and it has to tell to the base station that it is got stuck, then this auxiliary battery will supply for communication and communication antennas and powertrain. Driving motor. The rover uses a hubless hub is used because it is built onto the hub and no separate space is needed. Its features includes high torque at low speed and can be controlled over various speed and power ranges. Steering motors, we use 6 closed loop stepper motor for steering. Stepper motors are used because it is of high precision and it can operate at high holding time. Actuator, permanent magnet DC motor is used for actuating, and actuator is fitted at the front wheel of the rover and is used for lifting purposes. Motor driver, the motor is driven by a 4-switch inverters, and its speed control is done by PID algorithm with using multiplexers and adders instead of microcontrollers. Next is the battery management system. Like battery management system takes care of the battery, and it continuously monitors the temperature and reports back to the controller. It consists of sensors to monitor the temperature, and it evaluates the battery's SOH and SOC. When the SOC state of health deteriorates, it collects the data and sends to the controller, and the proper action will be taken. Converters, DC to DC converters are employed between battery and cell components to boost up or boost down the voltages. We use a series of SPR converters, and it operates at voltages between 18 to 40 voltages. Thermal management system, it is one of the crucial system, and as we are in Planum, Australia, the thermal management system should be proper. We implement the following following techniques. The electronics are housed in an aerogel enclosure. Aerogel is mainly used because it can retain temperature for a longer period of time, and the below the circuitry, a channel of copper channels will be used, through which freon hot coolant will be passed to heat the electronics. Cooling electronics also will be passed on a different channel to cool down the electronics when temperature increases. To prevent gas condensation caused by low ambient temperatures, space heaters used of ceramic materials are used to keep the motors dry. And embedded systems will be explained by Shubhilaya.
Hi, I'm Sudhilaya. While coming to embedded systems, we used Pentium 3 processor, which is a 32-bit cross 86 architecture radiation hardening processor. Its features are it can withstand harsh environment of polar regions on Mars. It has a clock speed of 550 megahertz to 1.2 gigahertz, and it has a memory of around 4 GB of DRAM and an 8 GB of flash memory. And it is an its auxiliary processing functions are it can assist the system process pictures from pairs of 10 cameras. The RTOs used are far left. Now coming to communication, a conical phased array antenna is placed at the rover and the omnidirectional antenna is placed at the base station. Conical antenna is used as it has high gain, high signal to noise ratio. The transmitters present in the antenna are phase shifted electronically, which helps in compensating the instability in rover's motion. Solid state power amplifier at X band is used to provide high precision gain and efficiency. An X-band transponder with couplers is used to avoid interference between the transmitter and the receiver. Of course, there might be some natural phenomenon like solar storm or dust storm that affects communication, causing data losses. So we came up with a solution which is quantum communication. It is a new approach which we can try implementing, where the data loss prevention is overcome with the help of quantum cryptography. This cryptography uses quantum entanglement phenomenon. Here, a pair of entangled photons are generated, where only one of these polarized photons are sent to the rover. Then the other is retained at the base station. Due to entanglement, the change in the state of one photon causes disturbance due to superposition, results in the change in the state of other. Thus, any interruption due to obstacles in the Martian atmosphere is easily detected with the change in photons. Next will be continued by Janvi.
Okay, now we are coming to the navigation subsystem. First, we'll discuss about the equipments that are helping in this process. We are using 2 stereo vision cameras for deeper perception and increased field of view. Then we are using 6 hazard cameras to overlook the ground level obstacle detection. To support these cameras, we'll be using this headlights and 2 blue laser lights. And the halogen lamp is used for the hyperspectral camera that is used for science tasks. Now we have used path planning algorithm. The path planning algorithm that we have used is goal-based vector field path planning. We have used this because it is a single computation algorithm, which has less processing time and power consumption is also less. The whole map is divided into n grids, where each node is divided into n nodes. The whole map, we first create a cost field based on the terrain, which places are accessible and which places are not. And then we generate an integration field from this cost field based data. And then we create a flow field where using these values from the integration field. So it shows the closest path to the destination based on the vectors which point towards the direction. So to optimize the algorithm that we have used, first we have used a convolution kernel. A convolution kernel, we use a kernel is convoluted with the existing cost field to receive a better flow field, which finds the shortest path in the most easier way. Then to avoid obstacle encounter, we eliminate all the nodes which are close to the obstacles. So the risk of encountering 2 obstacles are low. And then to reduce the pixel discrepancy, we use Lucas-Canades method because it produces more accuracy and it also it lessens the discrepancy. Then due to this, there might be some slipping in the wheel, soil wheel interaction. So to reduce that, we use we use an algorithm to forecast the soil wheel slippage and approximate the deviation in the path due to it.
Next come future human civilization. So far, we have tested only the possibility of life, water, minerals, etc. on the surface of Mars, but it is high time to enter Mars by establishing more hospitable climates. So we have come up with two unique approaches. One is making biomineralogical bricks. Here, a lot of dust is present in the Mars atmosphere. So we can collect this, and with the help of micro, we can bind this dust and make construction materials. The next is CO2 energy generation. There are a lot of dry ice present in the polar region of Mars. So by moving it to the furnace and heating it with plutonium-238, the pressure is increased inside the turbine. Once it reaches a threshold level, it is used to rotate the turbine and generate electricity. This concludes our design of the rover. Now we are open to questions.
So,
Yeah,
can I go
guys.
first, please? Yeah, go ahead, sir. Go ahead.
Yeah, Pranav. Yeah, guys. So that was a good presentation, and you just finished in the exact time. So yeah, so I would start with a question one topic which I saw in your report. So there you have given one paragraph to, like, how will you detect the sample site. So I want to know more about that. So how do you want to detect the sample site, and what are the first experiments you want to perform there? What is your target once you detect the site? After that, what you are going to do with the soil or the atmospheric analysis?
So we'll be collecting samples. We are doing it in two different methods. First, using the arm. In arm, we have kept a hyperspectral camera. We will be using shortwave, infrared and near infrared region frequencies. We use IR spectroscopic sensor. It will detect the absorption, transmission, and reflectance of the minerals. Each mineral have their own properties, how it will react with infrared sensor. And the hyperspectral camera will detect the frequencies, and using AI, ML, and DL, we'll be mapping all the data that we have received, so we can.
I got all those points. I just want to know, like, how are you going to select the site? Like, this is the site from where I will collect the samples. So what are the parameters you are considering for that site? Like, when do you consider a site to be suitable to collect the sample from that site? So first that thing. And then once you select the site, suppose I select a particular site, then I have to perform the experiments. So what are your main experiments there? Like the first experiment which you will perform there? Because there are so many experiments which you have listed in your report. Most of them you have shown in your presentation as well. So I just want to know, like, how do you select the site?
So first, mineral and fossil reduction is being done. Then we'll be checking whether any interesting objects or some interesting things are there, like craters or some different color soils are there. So these using ML and DL, first using camera will be detecting, and after that hyperspectral camera imaging will be using that for.
So basically, to select the site, you are going with the physical features like the craters or different texture soil, something like that is there. So you select that site as the potential area to collect samples. Right?
Interesting geological features will be checking. So from there we'll be collecting the soil.
Okay.
So I have a follow-up. Yeah, I just have a follow-up question. Yeah, sure. So you mentioned that you will select a site, right? So in the report, it's mentioned that you will be looking for methane and carbon dioxide levels. Are you looking for any other gases, as well as why specifically methane and carbon dioxide? Because they are naturally present on Mars, right? So how will measuring methane and carbon dioxide tell you about if life is there or not?
Sir, it is not. It's the carbon dioxide and methane levels. We have not taken that for just the seeing if there is life or not. We are those sensors we are using for how much level it is there, and if at all we are making any human if at all there is going to be any civilization there, what kinds of levels are there. If you know the levels in prior, what kind of measures can be taken so that it can be useful for human civilization. We can make it adaptable for the human civilization.
So you are not using gas measurements to infer anything about biosignatures?
For biosignatures, we are using spectroscopic methods, and we are using oxygen sensors. If there is any trace of oxygen present on the Mars, that we are using for checking if there are any microbes or biological signatures present on the Mars.
Okay, thank you.
Thanks.
Yes, I have two questions primarily. One is I saw in the drive systems you had mentioned you're using multiplexers and adders instead of microcontrollers. Any particular reason why did you decide to go that route? Hello.
Am I audible?
Yeah, you're audible. Go ahead.
Yeah, for computation of information.
Pardon me?
For computation, sir.
No, so why multiplexers and adders instead of microcontrollers? What is the exact thought process behind it? Like why did you, because there is one general protocol and there is one multiplexers and adders might work, but what was the idea behind that, or was it just something that you felt would be a better way to do it?
Sir, to measure radiation and the computation, like power will be taken microcontroller. We should separately power for microcontrollers. Multiplexers and adders, power consumption we can reduce, and computation power will be less.
Okay,
Yes.
not convincing, but okay, fine. You guys probably can work on that later. But the other question was, I saw that in your software stack, how are you going about the autonomous navigation part? I don't think you spoke much about that. What is the specific? You mentioned the sensors that you had on board, but what is the exact way you're going about autonomous navigation? And follow up to that, in I think a couple of slides you mentioned you're using MLDL and all of those things. Those are like very generic. Can you go more deeper into what exactly are you doing with MLDL, to even with the science task, or even with like what are you doing? Like what's the point of machine learning or deep learning in that place, and what kind of data are you extracting, and what parameters are you using to extract the data for both autonomous navigation as well as your science task?
Am I audible?
Yep.
Okay, so firstly, coming to autonomous navigation, we use goal-based vector navigation. We select a target place as we traverse, and then we go to that. So it's basically using stereo cameras only. Autonomous navigation is being done. So
using stereo cameras, what are you doing? How are you localizing the robot? How are you avoiding obstacles? How are you overcoming craters? What is the plan, or how is all of this coming together?
Using convolution kernel only, we are doing obstacle detection, and the coming to navigation part, it is as we mentioned, it's the algorithm. Like we basically generate a heat map, and then from the heat map we generate a 2D grid, and each grid is being giving it a value corresponding to the distance, the target distance which is set. I mean, the target node which is set, and according to that, we check the neighboring nodes, and we check the distance between the current node and the target node, plus the distance between the adjacent tiles. If it is more than the distance between the selected node and the target node, then we ignore it. Otherwise, we change the current node to the selected node, and then we add it to the list, and that's how the whole process is being done. We add as we traverse, we add it, and then we remove each current node one by one, and finally until the whole list is empty. So that is.
But what are you using to know the position of the rover at a given point? Like, how do you know that the rover has traveled 10 centimeter or 15 centimeter or whatever it is?
To know that,
How do you know the current position of the rover? Like, okay, you have an end goal, but to go to that end goal, you need to give some command to your motors, right? On what basis would you know that, okay, this is where I'm standing and this is where I have to go? So I need to, my wheel velocities have to be this. How do you know that?
Since the start, keep track on the movement of the rover.
Yeah, using what? What are you using to track the movement of the rover? Like what sensors, how is that data being fused? What is the software stack doing? How do you, what sensor data are you using for all of this? I'm asking about that thing.
Robotics sensor.
Okay, probably yeah, just probably look into that a bit more. I think otherwise good presentation, guys. Yeah, just these couple of things I had in my head, but yeah, I'm done from my side.
Yeah, others, Utku, do you have any question? You can proceed with that.
So for the localization, we can use wheel odometry for localization.
Okay, got it. Cool. Yeah, I think we're running out of time, so I do not have any follow-up questions right now. Sagar, you can continue.
Yeah, so is there anyone else who has questions?
Just a quick question. So in the report, you have mentioned that you will be making bricks using microbes. So like, can someone elaborate that a little bit, and where did you get that like idea from? Yeah.
So, sir, am I audible, sir? Hello. So
Yeah,
the main idea, sir, it's actually a new article which the whole brick the concept was invented was not was an ideology developed by IISc Bangalore recently 3 months or 4 months ago, sir. So they are using this bacteria which is when infused with the Martian soil, which can be used to convert it into bricks. So we used that idea. We thought it was a fresh idea done by our Indians, so we implemented it in our report, sir.
Got it. Thank you.
So thank you, sir.
Yeah, so I think that's it. And so guys, it was a good presentation, and we really liked it. And I hope you continue the same work in coming editions as well. And it was great to have you. And once we conclude the finals, we'll be sending you remarks from the other side, so that you can improve your design in the coming editions. I really like the things which you have used, but I think there can be some more clarity, of what you're doing there. I still feel there's a lot of scope for improvement there. So yeah, that's it. Thanks a lot, guys.
Thank you, sir.
Yeah, now you can leave so that the next team can join. They are waiting.
Okay, sir.
Thank you. Yeah, so hello guys, am I audible to you all?
Yes, sir, you're audible.
Yeah, hello guys, I welcome you all to the IRDC 2020 finals. And you are the second team of the day. And I think it's your first competition. So it's good to have you all. So before you start the presentation, let me remind you certain guidelines. You will have 16 minutes to complete your presentation. That would be followed by a 15 minutes Q&A session. During the presentation, 4 of you can speak. And after it, all of you are allowed to answer a particular question. So now you can start.
So before starting, I'll just request the other team members to just check their mics once. Just say hello once, please, team guys.
Hello, am I audible?
Yes, okay. Yes.
Hello.
Yeah, audible. And Ronik?
Hello.
Okay, you're audible too.
Hello. Hello.
So shall we start?
Yes, you can start now.
Okay. So good evening, dear judges and the audience present. You are witnessing a live event, the first of its kind. This is Project Polaris, the first ever exploration mission on the polar region of Mars, under the banner of International Rover Design Challenge 2022 and in association with Space Robotics Society. We, Team Robo and ITR, without further delay, ask you to join us. Let's take off. The results we expect from this expedition could be anything. Hence, it's important to be prepared. We present to you the various subsystems present on our rover, which enable this expedition. The chassis, the drive system, the power unit, the robotic arm, the cryobot, which is called THEA, navigation and communication modules, and the onboard laboratory. The grand weight of the rover is about 350 kgs, which includes the independent deployable cryobot. The maximum speed of traversal is 5 centimeters per second. During our mission, we are expected to encounter chilly temperature ranges going as below as minus 140 degrees Celsius. At this temperature, common earthly materials fail miserably. Even stainless steel becomes brittle and incapable. To counter this, we have used an aluminum and titanium alloy due to its performance in extreme conditions.
What goes inside a rover? The electrical subsystem. The power source supply electrical power to various subsystems via surge protection module. There are 5 subsystems which require different voltage levels and hence has been given power accordingly. The control signals are sent by a central onboard processor and various other microcontrollers present in their respective subsystems. A number of motor drivers control motor or linear actuators in these subsystems. Power surge protection. Going into further details of power surge protection circuit, it comprises of external skill switch, which is controlled by operators from the base station. It is powered by a separate power source, hence it has the capability to turn on and off the entire rover system in case of any malfunction. In addition to that, circuit breakers which are triggered by overvoltage and overcurrent also cut off power supply and work autonomously. More safety devices used in rover. TPS, a high-performance thin film product, is being used to ensure that electrical current from different systems will not interfere with each other while also protecting delicate cable systems from harsh Martian environment. Reflective cover, added as an outer shell for reflecting back direct electromagnetic radiation, which could potentially induce magnetic field and eddy currents in electrical subsystems. PoE-SP, Power over Ethernet Surge Protection. It is engineered to protect PoE or non-PoE devices with connection up to 1 Gbps. Power systems. Lastly, the power source of the rover. In an environment with minute amount of sunlight and frequent dust storm, relying on solar panel can be catastrophic. A lithium-ion battery acts as a primary source of power, a single cell of which provides about 12 volts. The rover is also equipped with an RTG, which provides backup power as well as charges the battery slowly. Its discarded heat is utilized to keep the system warm and under the operating range.
Looks like all the setup is complete and the countdown has begun. It's liftoff. In a few months, we will reach Mars and you will witness a superb expedition. Till then, it's goodbye, Earth. Oh, how fast that time went. We've already entered Mars vicinity and are about to touch down. The landing site is between 74 to 77 degrees south in latitude. We are going to investigate this region of Planum Australe. To make you aware about the environmental conditions here, the temperature range is -60 degrees and is falling constantly. Winds blow at huge speeds and dust and snowstorms are expected. There is a high risk of radiation as well, and the pressure is supposedly 6 times the normal ambient pressure on Earth.
Establishing communication. The first job for Polaris the rover after landing must be to localize itself in the environment and set up communication with the base station located at some distance. With the coordinates known of both landing site as well as base station, we can easily assume one of them as an origin and get to know our position. And we will be considering base station as the origin. IMU can further be utilized to measure rover spatial position in the Mars plane or in 3D space. In case there is a secondary base station present, with no need for operators, it's also possible to triangulate our position using radio frequencies. Communication system used in this rover is Ubiquity's Rocket Biz, which uses 5 GHz frequency band. The high frequency makes it noise immune to radiation. It packs enough range for communicating in our mission. In case of loss of communication, there are options to switch channel or increase channel width. Also, a secondary communication system which communicates at 900 MHz frequency band is present. Exploration. Communication check. Clock is set at 00 hour. The mission henceforth begins. In a bid to explore and map the entire area, the rover make use of vision feedback, including depth image. With algorithms like RRT or custom developed navigation algorithms like moving in a spiral, the rover is able to generate a 3D map and a 2D grid map of the region, documenting obstacles as well as visual features via real-time appearance-based mapping algorithms. A semi-custom stereo camera has been mounted on the rover with immense capabilities.
Moving on to the mechanical aspect of our rover. The chassis is an octagonal frame made up of rectangular tubes of aluminum and titanium alloy. The shape is optimized to carry all of the subsystems with decent stability and uniform weight distribution. The frame is covered with alloy sheets of up to 8 mm thickness for added protection from debris and landing conditions. The gross weight of the chassis is around 33.7 kg, and it provides an excellent and sturdy framework so that all of our components can be mounted and traversed easily. One of the biggest challenges of the Martian exploration is the unforgiving harsh terrain made up of boulders, loose soil, and in our mission, icy surface. To navigate easily, our rover uses a modified version of a rocker bogie suspension, whose effectiveness is proven with rover solidly on Mars. The drive uses 2 pairs of deformable alloy wheels capable of absorbing vibrations and minor shocks. The wheels are driven by Maxon BLDC motors coupled with a high reduction gearbox, providing a reduction of 400:1. Our system also uses a secondary drive, which is to be engaged when traversing on the icy polar region. The rover will perform analysis on soil and ice samples in the onboard laboratory. To perform this, a 4 degree of freedom arm is employed. The arm will extract samples from its environment and transfer them into the laboratory. The robotic arm uses cycloidal gearboxes at the shoulder, elbow, and wrist joint, which provide very high reduction in a compact size. Similar to the rover body, the arm tubes are also made up of the aluminum and titanium alloy. The end effector of the arm is equipped with a drilling module, which uses an auger-like drill to collect soil and ice sample. The unit also contains cameras for imaging the soil structure while collection. Another microscopic camera gathers the microscopic data of the samples. So after performing the analysis on the soil region, our rover actually moves toward the icy region, and it has to cross a region of soil and ice interface to move towards the polar region. To make this traversal easier, a hybrid drive system engages the Caterpillar drive system to increase the traction and providing a better control over the slippery surface. When we are actually traversing on the rocky terrain, there is a possibility of dust and debris lodging inside the caterpillar track, as we have a lot of hinges and moving parts. So during that phase, half of the caterpillar drive will be covered by a expendable cover system. And after we reach the region of polar ice caps, where there will be considerably less amount of debris, the cover will be ejected and the whole caterpillar drive will be engaged to the ice surface. Now that our rover is in the extreme chilly Martian regions, the heating system becomes of prime significance. Our rover is protected by a passive as well as an active heating system. A layer of multi-layer insulation traps the heat generated inside the body by the CPU and other electronic components. This layer is composed of an aluminized polyimide layer, a layer of lead, and an aerosol layer. The lead layer provides protection from external radiation, while the aerosol acts as a really good insulating material for trapping the heat inside. We also have an active heating system, which uses the residual heat from the RTG and through a network of copper conduction coil, redistributes the heat towards important components of the rover, like the computer and our laboratory unit.
Cryobot. Since our robotic arm is only capable of taking samples from up to subsurface, we are introducing our subsystem Thea, that is a cryobot capable of going up to depth 10 meters. It is used to take images of ice layers and collect gas samples data at different depths of ice. The obtained data is transferred to the receiver, placed at the surface level, and the receiver is used to transfer the data to our base station. The receiver receives the data from cryobot using a cable which is insulated with aerogel to trap heat inside and protect it from the extreme climates. To ensure a cryobot can function in the harsh environments, it has an RTG equipped in it which provides the heat required for melting the ice, and under the action of its own gravity, it reaches the required depth. It has walls insulated with aerogel to ensure no heat is lost through its lateral surfaces. First, the rover finds a suitable location for the deployment of the cryobot. The cryobot is deployed, and under the action of its own weight and using the heat produced from the RTG, it digs a hole inside on the surface and reaches the required depth. As it goes through the depth, the melted frost, as it consists of mainly dry ice, sublimes, and the gases are analyzed using the CO2 sensors present inside the cryobot. The the cryobot also consists of a micro cameras which take the images of the different layers of the ice, and using the different layers of the ice, and by using layer dating, we can estimate the difference between the edges of the top layer and the target depth. For deployment of drones in plenum astral in future missions, the climatic condition of the environment are very important. To get the required data, we are using nitrogen thermometer for calculating the temperature of our environment. Since most of the thermometers on Earth are incapable of measuring the temperatures, nitrogen thermometers are the perfect solution, since they can measure the temperatures up to minus 210 degrees Celsius. Wind speed, one of the important parameter for drone deployment, is calculating using an anemometer, which is on board and which is its important components are insulated using aerogel. Moving on from the aero analysis, we come to our regolith analysis. that is soil sample analysis, which is part of our, which is one of our important objective of the mission to detect the microbiology in Mars surface. The regolith analysis utilizes spectroscopy to measure, to determine the intensity of various components in the soil sample, that is the proteins, and is used to determine the presence of these proteins by comparing the data with existing data on Earth. Ice core analysis. Another part of our mission is to measure the climatic changes on Mars. Ice core analysis equipment is used to measure the concentration of CO2 in different layers of Mars, and by comparing the changes in CO2, we can determine the changes in the climatic condition of Mars.
So after drawing conclusive results from the scientific analysis, Polaris sets off on its journey back to the base station. A simple go-to-goal as well as obstacle avoidance based on the local 2D or 3D cost map ensures that the rover reaches base station autonomously. It is greeted by the astronauts from Team Robo. A gruesome session of constant monitoring, investigation, and analysis finally ends on the most positive note. We encourage the viewers to meet our astronauts as well. Our team structure comprises of a small number of people handling various subsystems like electronics, mechanical design and simulation, as well as the science and astrobiological team. Thank you, and we welcome our questions now.
Thank you, guys.
Hi.
So that was a good presentation.
Yeah.
And
Thank you.
yeah, now
very
judges,
much for the-
you can proceed for the questions.
Can you hear me?
Yeah, we can hear you.
Oh, okay. So I have a question about your landing site. Can you show it once again? So my question is, why do you want to land on the slope of the crater? So I think you need a flat surface for landing. So I am very interested. That's why you have chosen this specific place.
So actually, we will be trying to land close to the crater surface, which will be somewhat planar. But our major point of interest will be the crater itself, because we are trying to find the microbial life activities, and in the topological features of crevices and different folds of soil and other topological layers, the probability of presence of life increases manifold as compared to the planar region. And as our mission time is significantly low, that's 20 hours, and considering the actual Martian environment, our rover is actually restricted to very low speeds. We have to make our landing as close to the crater site as possible, so that we can immediately explore the crater region.
Yeah, I understand. I think that crater is a good site, but I think that you should mark the place maybe next to the crater for your season. I know that Hubert has some questions about mechanical design. So Hubert, do you want to ask?
Yes, ma'am, that's acknowledged.
I have also a question. If you can hear me, well, okay. What will happen if your caterpillar fall off the wheels? Do you have some solution for that if the failure occurs?
If our caterpillar drive fails, we actually have designed our rover to be capable of driving on the four wheels itself. We can disengage the wheels using the linear actuator, and we can drive along with the four remaining wheels actually. So that's a rover system.
Okay, so another question. You have a heating system in your rover. So what will happen if you will have a too big temperature in your chassis? Do you have some solution to get rid of that heat outside?
Actually, we have expected that when we enter into the polar region, the chances of the heat spiking over a certain threshold is somewhat really low. That can be possible in an extreme scenario, or unprecedented situation. But there, using the heating coils, we can actually disengage the, as you can see in our model, if you can navigate to the part, the RTC is actually exposed to the surroundings. So if in case the temperature rises above to an uncertain level, we can actually disengage the heat transfer unit, the copper conduction coils, so that most of the heat actually is dissipated to the environment instead of inside the rover. But we have considered the probability and it's very less likely.
Okay, and the last question is, why did you use 4 degrees of freedom of robotic arm? And can you justify if that will be sufficient for the rover operations?
Actually, we first started with considering 3 different configurations, one with a 3 degree of freedom and 4 and 5. Then after performing some simulations in Adams, actually, we finalized that 4 degree of freedom is the least amount that will be needed. That's more suitable for our operation. We just have to collect the soil using the drill head and take some images. We don't need that much freedom of manipulation. So 4 was like an optimum choice where we could settle down.
Okay, so if you will want to take a little bit of, let's say, dry ice, do you have the possibility to take it from the slope or from the rough terrain? Because if you have 4 degrees of freedom of manipulator, the effector can only tilt. It cannot roll. So if this situation happen, what do you plan to do?
First of all, we'll actually keep our focus on collecting soil from the ground level itself. But in case we want to collect the sample from a slope or ridge, we can actually orient the rover itself in that direction, so as to facilitate that particular orientation required for collection. The whole rover can rotate. It has a well executed steering system, so that was unnecessary on the robotic arm itself.
Okay, thank you.
I have a question. So like it's about science. So what is your strongest instrument in the rover that would be able to detect a biosignature? And what kind of biosignatures are you expecting considering the site? So
we are using soil sample analysis equipment for measuring the microbiology of the Mars. It measures the proteins present in the microorganisms, and it basically uses infrared rays which passes through the sample and a detector which collects the intensity received. By comparing the data with the existing data on Earth, we can conclude the proteins present on Mars, and by which we can conclude that biology is present in Mars.
And what is the principle of that? As in, how is it detecting protein specifically and not others? Yeah.
The infrared laser is coded for a specific wavelength, which is only some proteins are capable of absorbing those proteins. And when the sensor receives the intensity of the received laser and plots the data, by using Raman shift, we can find the appropriate protein which it corresponds to. To get the accurate results, we are using 4 lasers set it at different wavelengths to not leave a chance that we missed a certain protein which was present.
Thank you.
I have a question actually. Oh, okay. Yeah, go ahead.
Okay. My question might be out of the box, and it's about environmental effects. So how do you think your rover might respond to okay, let me put it this way. You said you used aluminum alloy for your design. As far as I know, corrosion resistance for aluminum alloy is relatively average, right? And since we're on Mars, some climatic chemical reactions may occur during your mission time. And if this happens, what kind of precautions do you think that you can take?
So actually, for protecting the rover frame and major structural components from corrosion, first of all, there is a layer of protection for the layer that we are using for insulation and protection from radiation actually also acts as a protection layer from external chemical hazards, not chemical, but that hazards. So first of all, the frame of the chassis is well protected by this external layer, and remaining on the rocker body and other structural parts, we actually have this layer of aerosol everywhere. So coming in contact with corrosive nature of the Martian environment is likely in the case of some mishappening, like if some of the components breaks apart or the aerosol layer chips away. So corrosion resistance is actually implemented in this way. But from the design perspective, it's somewhat certain that there won't be a direct contact of the aluminum alloy that we have used to the Martian environment. And the specific alloy that we are actually using, that's aluminum 7475T7651, is actually somewhat highly resistant to corrosion, and it also withstand the Martian temperature ranges really well. This was only some of the materials that actually performs really good at the temperature ranges we require, so that we selected it.
And sir, I would like to add that for the points like the outer tire of the wheel and the chain drive, we have used authentic steel type 304 that is somewhat heavy but provides more strength and rigidity compared to the aluminum.
Okay, thank you.
Yeah, I have a question. Am I audible?
Yes,
Yeah,
yes.
so yeah, I want to know that whether you have any kind of system to scan the area where the cryobot is going to go. What if there is a obstacle or stone after a certain depth? So do you have any mechanism to either avoid it or detect it beforehand before going into the snow?
I'll say that we don't actually have an active system to map out the area where we'll be deploying our cryobot. So the first step that we implement to ensure that our cryobot is in a free, safe zone is that our rover will travel deep inside the polar regions, where we are actually trying to the cryobot will try to reach up to a depth of 10 meters, and our strategy is that we'll try to reach deep inside the polar region such that the layer of ice is greater than 10 meters with certain certainty. We don't really have any active system to measure that beforehand.
Okay. So maybe you can work on that a little bit before, scanning the system before. Because if the cryobot hits an obstacle, it might get damaged, right? Because there is no drilling system in the cryobot present already. So yeah, maybe you can look into that one.
Yeah, so adding to the question which Neil has asked, in your report, I've seen there's one risk analysis, and you have written down 10 different points there, and then likelihood or severity also you have taken into consideration. So I'm curious to know, how did you reach those readings?
Actually, we concluded most of them from our previous rover building phases as we test our rovers on the live environment right here. So some of them are somewhat obvious from the testing conditions, and others were actually derived from looking at the NASA Mars rover missions, what kind of damages they were subjected to, and in the polar region what we can expect. So it was kind of extrapolating from all those information, and mostly in this way.
Yeah, but the polar regions haven't been explored the way we plan to explore in IRDC. So only landers have been there so far, that too in limited areas. And the duration also.
Actually,
like, what is the mission duration? Total duration of the mission?
That's complete 20 hours.
Okay.
So
because some of the
one of the
readings will
parallels,
change once you change the mission duration, right?
For actually getting familiar with the environment that we might encounter on the Martian polar region, we actually looked at the polar region of Earth itself, like how the exploration is being done in Antarctica and all, so that some parallels can be created. As we have really no actual idea of the Martian environment, but we are trying to predict some of the points from our own understanding and all.
Okay, have you taken some measures or have you included some practices which might reduce this risk in your design?
First of all, for example, in our heating system, we have considered the temperatures to go well below -140 degrees Celsius itself in the calculations. And from the terrain wise, the idea of implementing caterpillar drive actually came from the fact that we won't be encountering any liquidy mess around there. Most of the ice is actually dry ice. It will actually sublime directly. So the caterpillar drive was designed in this way to traverse that terrain. And then we have one of the scenarios that was considered, that due to the icy region, there was a chance of our cameras getting damaged by the reflected sunlight. It happens in icy regions on Earth itself, but there was no way to actually gauge how much of a problem that is. But still, we have implemented certain filters and polarizers on our camera lenses so that we can stay protected from these scenarios. But again, we are not sure about the probabilities, so it's all about prediction and suitable implementation.
Okay, guys, thanks a lot. It was a good presentation, and you were good in Q&A also.
Thanks a lot.
And
thank you, sir.
Yeah, I hope to see you in upcoming competitions as well. Thank you very much.
Certainly. Thank you, sir. Thank you.
Yeah, you may leave now.
Thank
The
you.
next team is waiting. So hello guys, welcome everyone. And before you start, let me just take you through the guidelines. You will have 16 minutes to present your design, and after we will have a Q&A session for next 15 minutes. During the presentation, 4 of you can speak, and during the Q&A session, all of you can answer a particular question. So yeah, and if you exceed the time of 16 minutes, I will have to stop you. So whenever you're ready, you can start.
Good evening, judges and organizers. We are Masterful Manipal from Manipal Academy of Higher Education, and we are proud to showcase our design for IRDC 2022. Masterful Manipal boasts a diverse background of knowledge in 5 domains, hence its 5 subsystems: research, mechanical design and manufacturing, electronics and control, AI and automation, and finally life science. Our mission aims to explore the frigid soil ice boundary regions of Planum Austral as a potential storehouse for past and present biomarkers, owing to the cryopreservation abilities of polar ice caps and seasonal carbon dioxide frost. Our solution focuses on implementing revolutionary robotic technologies and deploying auxiliary modules designed to execute specific tasks not limited by the constraints associated with large vehicles such as the Rover.
Our mission consists of 4 primary mechanical systems. The first is the drive system, which comprises the chassis, suspension, and wheels. The monocoque chassis is designed with a high entropy alloy to enhance mechanical properties at cryogenic temperatures. Dimensional capacity is optimized to fit all auxiliary modules and maximize surface area for solar panels. Additionally, the chassis is thermally insulated by an embedded layer of aerogel. To traverse the unpredictable and harsh Martian terrain, we designed a custom active suspension inspired by the Sherpa mechanism. Each of the independently controlled legs features 4 degrees of freedom, actuated by brushless DC motors and harmonic gearboxes. The joints allow the Sherpa suspension to manipulate parameters such as stiffness, damping coefficient, suspension travel, and geometry, thus providing the rover with higher maneuverability and reconfiguration capabilities. This allows the rover to rapidly manipulate its center of gravity and support polygon. Each wheel is capable of switching between a conventional wheel configuration, which improves efficiency in terms of time taken to traverse a given region, and a trapezoidal track configuration that is optimized for traction, providing exceptional performance in ice-covered rocky and sandy terrains. Interconversion between the two configurations is achieved by rotating the support members and actuating the sprockets radially to switch between a circular and trapezoidal cross-section. The primary source of power on the rover is a multi-mission radioisotope thermoelectric generator, or MMRTG. It is a compact, light, safe, and reliable nuclear source of energy that gives a continuous power output irrespective of environmental conditions and fuel supply. Solar panels with triple junction solar cells are used, which provide up to 32% efficiency, supplying additional power to the rover. The rover's energy storage system consists of lithium-ion rechargeable batteries used to meet the rover's peak energy demands. The Mars exploration rover lithium-ion batteries are compact with high energy density, power output, and can efficiently work at low temperatures. Heat ejected from the MMRTG in the form of radiation is converted into electrical energy by employing TPV cells with 40% efficiency. Aerogel sheets within vacuum-jacketed enclosures help maintain a constant temperature within the chassis. The excess heat is ejected outside the chassis through aluminum ammonia constant conductance heat pipes. A part of that heat is used to increase the internal temperature of the electronics module, determined by a hardware PID controller calculating the amount of hot gases diverted by the valve. The error differential is obtained by thermocouple readings. Additionally, a heat rejection system is employed to prevent the overheating of electronic components. The rover houses an advanced energy management system, or EMS, to optimize energy consumption according to the mission plan. The primary function of the EMS is to protect the battery cells from damage caused by overcharging or over-discharging. It consists of a battery charge regulator, a battery discharge regulator, to monitor the charging of the batteries from the MMRTG and solar panels. Dynamic power scheduling is used to prioritize loads according to their real-time energy consumption.
All the rover's modules are interfaced with a single board computer, Jetson Orin, chosen due to its wide array of I/O interfaces and multi-programming capabilities by using its GPU and CUDA cores. All subprocesses of each individual module are run on separate threads to enable mutual exclusion and constant feedback from sensors. Autonomous traversal functionality has been implemented using a state-based Markovian process based on environmental factors and mission constraints. The probability of each state is dynamically calculated on sensor input from the stereo camera, IMU, and other onboard sensors, augmented with multiplexing logic. It is then used to transfer from one state to another. In order to ensure safe traversal and path planning, goal-oriented action planning, or GOAP, has been utilized. A final goal state is defined as either an obstacle avoidance parameter or a destination pose. The GOAP structure then iteratively computes cost towards the goal state, updating the cost dynamically after each step up to a point where the goal state has been achieved. Upon stabilizing at the goal state, the control handle from the GOAP structure is withdrawn and allocated to other submodules, ensuring a stationary rover setup. We developed a simple GOAP-based structure emulating the decision tree using C++ and tested it for proof of concept on a stock simulation. We have developed a custom n-nodal cluster-based localization algorithm to localize the rover and the drone in real time. Inspired by GNSS, the concept of pseudo-ranging using long-range ultra-wide band-ranging modules has been implemented. The deployed auxiliary modules form nodes of a distributed ground space network with their locations calibrated using an onboard high-rise-like software, which updates the location of nodes every 1 hour and 41 minutes. The distance from each probe and the base station is calculated, and the corresponding spheres in a Cartesian space allow accurate localization of the rover and other auxiliary modules. The rover has an active suspension, which helps maintain high ground conformability and achieve good traversal. Each link is independently actuated, similar to a 4DOF robotic arm. Each degree of freedom is manipulated using inverse kinematics. The overall controller has 6 instances, one for each link. There are cameras on each link directed at the ground. It calculates the goal end effector position using image processing and sends it to the controller every second. Three controllers have been designed to ensure smooth traversal of the rover. The Ensure with Contact Ground or ECG controller is a wheel altitude leveler which ensures perpetual wheel ground contact. The roll pitch adaptation or RPA controller is a fusion of two PI controllers which controls the pitch and the roll. The weight distribution controller or the WDC is a stabilizer which takes expected wheel normal force as input and maximizes chassis stability by trying to ensure equal weight distribution on each wheel. The estimate of the force offset required is dynamically calculated using the Moore-Penrose pseudo-inverse. A soft actor-critic model has been implemented to calculate the final pose of each leg. An actor network is complemented by a synchronized feedback critic model. Each action of the actor has a corresponding critic feedback which updates the value of the function. A temporal difference version of policy gradient has been used for the updation of this function. The pose computed by the SAC is then fused using an unscented Kalman filter with the outputs of the controllers.
The second mechanical system is the sample collection analysis module. The science module houses all necessary instruments and sensors to perform in situ analysis on board. The module comprises a SCARA arm and a multi-auger system to facilitate the collection of soil samples while preventing cross-contamination. Each auger is designed to reach a depth of 70 centimeters, and it uses a full stud mechanism to attach and detach from the SCARA arm. The rover houses multiple instruments for astrobiology, aerobiology, geology, and weather analysis. We have used the live detection immunoassay, or LIDIA, as a replacement for chemical assays, as it detects a multitude of biomolecules by conjugating with a grid of phenol antibodies. The biointegrator LiDAR instrument, or BILI, looks for organic molecules in the atmosphere using fluorescence produced when UV light shines on them. The ChemCam uses laser-induced breakdown spectroscopy to analyze the chemical composition of rocks and soils in the vicinity. Its microimager is used to closely study the texture and morphology. The BME688 measures temperature, pressure, humidity, as well as volatile organic and volatile sulfur compounds in the atmosphere. The Martian acoustic anemometer, designed specifically for the Martian environment, is used to study wind speed and other aeolian processes. The pyranometer measures the solar intensity the region receives.
The third mechanical system is the hammer probe. The hammer probe is designed to burrow into margin soil. It utilizes a reciprocating mechanism based on a modified Kamen follower to create the periodic motion that is used to pulverize soil and ice. A telescopic actuation mechanism deploys the probe and ensures that the probe is released perpendicularly close to the soil surface. The probes are powered by autonomously deployable solar panels. A thermocouple and a PTC ceramic heater are integrated into the hammerhead to maintain it at the required temperature. The hammer probe contains a subsurface camera, which uses a thermal camera coupled with the Raman microscope to detect heat signatures from life and then verify them by checking molecular composition. The BioFET studies samples from deep under the surface, which is more suitable for life, for the presence of biomarkers using a biological circuit. Further, a Hydra probe that measures soil moisture, temperature, conductivity, and pH also helps with the evaluation of the region's habitability.
The fourth auxiliary system on board the rover is a tethered drone, implemented for the dual purpose of localization and expediting site selection for scientific analysis. Each drone is a bicopter consisting of two arms that facilitate the implementation of two coaxial rotors on each arm. The drone is also equipped with a retractable landing gear, which helps vary ground clearance while deploying auxiliary equipment. Site selection is made possible with the stereo cameras mounted on each drone. This instrument helps keep record of visual data and identifies potential sites for analysis based on visual markers. Over the course of the mission, the two drones also deploy multiple puck antennas which act as cluster nodes in localization. An innovative tethered drone system is used due to the time constraints and the size of the region to be explored. The drones have a range of up to 400 meters from the rover and can perform independent analysis using onboard instruments. The drone explores the area with a radar, which can look through layers of ice and search for subsurface lakes. A visual camera is used to locate regions of interest for the rover to traverse and collect samples from. A bioaerosol sampler for aerobiology will connect any microbial particles suspended in air, which can be analyzed once the rover returns to the base station. To reduce weight, the drones are powered using a 10 ampere hour lithium ion battery housed on the rover with the power carried by a tether. An autonomous self-winding winch has been implemented, which ensures that the cable stays taut. The drone uses a Raspberry Pi onboard computer integrated with an onboard flight computer for telemetry. It uses brushless DC motors and an ESC for actuation. The drone uses the principle of thrust vector control to establish flight time stability and altitude persistence. Altitude input comes from the radar, whereas the XY velocity is calculated by differentiating the acceleration obtained from the IMU. The XY velocity compensation is used to calculate the upthrust, whereas a PID controller has been implemented for altitude regulation. For docking the drone, a fuzzy logic controller has been implemented, which takes a curved docking trajectory to ensure safe docking even when the rover is in motion.
The rover uses polarization reconfigurable antennas based on liquid metal tuning to communicate with the base station. It also communicates with auxiliary modules by acting as a node, forming a multi-hop system. In order to improve the quality and reliability of the communication, two collocated high-gain directional antennas with different response patterns are installed at the base station to communicate separately with the rover and auxiliary modules. These signals are then combined using the maximum ratio combining technique, in which the strong signals are amplified further while weak signals are attenuated. The radio signal path is vulnerable to multipath interference when communicated with the rover and auxiliary modules. To overcome this, we employ the concept of orthogonal frequency division multiplexing, which aids in the elimination of intersymbol interference while boosting signal-to-noise ratio.
With the mission being time-bound, every decision made has an influence on the success of the mission. Taking into account the fact that regions of interest in Planet Austral become more accessible during summer, we have assumed that the mission takes place during the summer. We begin our mission at the soil ice boundary, where we collect the first sample and deploy the first hammer probe. This will explore the subsurface, which is protected from radiation and has more favorable conditions for life. The rover then moves to the edge of the south polar layer deposits, which would be exposed to the seasonal CO2 cap melts. These are the layers of ice sheets which trap air from over the years. At the base of the cliff of the SPLD, it can collect basal sediments, that is the very first layers of sediments under the ice, which are a reservoir or a reserve of history of the environment of the region. From here, the drone is deployed to map the area. The regions of interest we primarily aim to study and find are eskers and starburst formations. Eskers are layers of sand and gravel deposited from glacier meltwater. You will thus carry sediment that possibly floats through liquid water, which is an epicenter for life. During the spring, pressurized CO2 under the surface bursts out in forms of geysers, bringing out sediments with it. These create formations called starburst or spider formations. Being sediments from the subsurface, these have higher potential of storing biomarkers. This region would have a higher likelihood of suspended biomolecules for the aerobiology investigation. Once the region of interest is located within the drone's radius, the rover is moved there for further analysis. The second hammer probe will be deployed in the region, which shows signs of a subsurface lake as located by the radar. Such a region will have more habitable conditions for extremophiles such as halosacrophiles, along with preservation of biosignatures. We thank the judges for giving us this opportunity to present our work. We look forward to any questions that you may have regarding our report and presentation.
Hello, I have a few questions. Like on each wheel, you have a possibility to turn it around. They are 4 degrees of freedom, like you can turn it around by motor at the end of the second link. So what will happen if one of the rover wheels will be blocked in perpendicular position to the rover movement in case of motor failure and so on?
So we specifically use brushless DC motors to prevent motor failure in this scenario. If the wheel is ever locked in a specific position, then the suspension link that it's attached to can be actuated because, as you said, it has 4 degrees of freedom. And also, we can, if the wheel is lodged somewhere, then we can always switch to track mode, between wheel mode and track mode, in order to dislodge it, since it changes its cross-sectional area, and that will help dislodge it from wherever it's trapped.
Okay, and the second question is, you have solar panels, batteries, and MMRTG, and like, why do you want to use so many sources of power? Like, don't you think your rover have to be redundancy in case of this exploration?
So our main power source is the MMRTG, which we are using on board the rover. In case the MMRTG fails, the auxiliary power sources will be the lithium-ion batteries on board. The solar panels are there to reduce the discharge rate of the lithium-ion batteries.
Yeah, but it's increasing your weight. So what about this one?
Can you please repeat?
Yeah, as Hubert mentioned, you have 3 sources of power system, so it influences your weight. So actually, you demand more power. So do you think that really it is a sufficient solution to have so many different solutions in one rover for quite short missions, I guess?
Actually, the thing is that we are using 3 MMRTGs, which supply a total of 330 watts. But unlike other rover missions which span for years, we are using many auxiliary modules which are working simultaneously alongside the rover in a very small mission duration of just 20 hours. Hence, at any given moment, we exceed the power which we are getting solely from the MMRTG, which is 330 watts. So to overcome this, we are also using TPV cells around the MMRTG to absorb the radiated heat by the MMRTG, and it is also reused to convert into electricity. And in case these systems fail, we use the auxiliary power source as lithium-ion batteries, and their discharge rate is reduced by continuously charging them with solar power.
Okay, thank you.
Yeah, I had a question. Am I audible? Yeah, so can you go to the slide of the legs part, the suspension part? Yeah. So in this you have used a brushed DC motor. So you will be needing a precise control of every joint, right? So why haven't you gone with the motors that provide precise movement like stepper or servo? And how are you taking the feedback from the DC motor to see if it has gone to the position you want it to do?
So we have been using brushless DC motors for actuation, and we are receiving the feedback using cameras mounted which on each specific link joint of the wheel and suspension. This is used for inverse kinematics calculation, which couples with the machine learning algorithm to add on to our calculation.
One second. I'm asking about the motor that is there. It is written DC brushed motor, right? In the joint.
So it's a DC brushless motor.
Okay. So it should be brushless. All right. So how are you taking the feedback from that? Like from the motor itself?
So we're using a camera to take the feedback. We're using a specific pixel location technique which calculates the specific pixels which are occupied in a given frame by the wheel, and that is being used to locate the specific wheel. This allows us to apply this for inverse kinematics further. To calculate the position of the wheel should be required in the coming temporal time frame.
Okay. And why have you chosen the brushless DC motor for that particular operation, and why not stepper or servo that provide you direct feedback.
So the motors, a stepper or a servo motor would provide us direct feedback. But the point being, these feedbacks will form. We have an active suspension, and each of this link in the suspension is actuated. So this means the number of dynamic transforms which should be increased for each specific link would be too many, and that would increase the compute. Whereas when we have a camera for feedback, we can directly locate the pixels, and when pixel location occurs, a specific padding frames are formed around it when surroundings are the same. These padding frames allow us to reduce compute, and the change in the pixels of the wheel allow us to process it faster, and any sudden jerks can also be minimized. That's where the soft actor critic model also comes in, which would help us. It's a all combined process where the model would help us reduce jerks, and to make sure that everything happens smooth in a fast manner, we use the cameras for feedback instead of relying on other modules feedback, where dynamic transform calculations from multiple links would take up a lot of compute.
Okay, yeah, thank you.
I have a question. Am I audible? Okay, I think I am. So I see that you're using Lydia, that is live detection immunoassay. So in that, I see that you have listed a lot of molecules that could be detected in your report, right? So if I were to give you an option, like I'm sure you won't be able to accommodate so many types of biosensors. So say you have to narrow down to just 2 or 3 biomolecules that you are looking for using that like biosensor, which one would you choose and why? Is my question clear?
Yes, so to choose the biomolecules, you would probably biomolecules that would signify extinct life or extinct and extant life. So for extant life, we have enzymes and nucleic acids, for example, because they have very few abiotic sources, which would clearly signify extant life. For extinct life, we could also choose like lipids and fatty acids. Fatty acids, in the absence of any easily degradable biomolecules such as enzymes, would indicate extant life.
Awesome, makes sense. Thanks.
Yeah, so I have a quick question. So what is the life of these 2 drones? Am I audible to you all?
Yeah, so the drones that we have on board the rover are tethered to the rover. So they can fly for, technically they could fly for the entire 20-hour duration because the batteries are connected to the motors of the drone, and the power is constantly being supplied from the rover. So, and they can fly within a range of 400 meters. So, and they serve the purpose of collecting visual data for scientific analysis and also deploying the AI modules.
So what all instruments you have on the rover? The drone.
We have a stereo camera that records visual data, and then we have a puck antenna, which is used for localization, and we also have a UWB module.
Okay, so how much time did you spend on developing your drone? Like how many days did you give to the entire project?
We spent 2 weeks developing the entire project. The drone itself, we chose to use it because we knew that the time duration for the rover to go on the mission was just 20 hours, and it could only traverse at a certain speed. And we wanted to look at all the available areas for scouting. That's why we have the drones.
Okay, good. So yeah, Pranav, Utku, do you guys have any question?
No, I'm good.
Okay, then I think that's it. So the presentation was good. The report was also good. I see some misrepresentation on the presentation. One was pointed out by Neil, and some comments as well. So from next time onwards, hide those things. And for the finals, create one more presentation where you don't have any comments or anything visible to the judges or others. So that is the one feedback which I have for you, and rest looked okay. So yeah, guys, thank you.
We sincerely apologize for that, sir. We did not expect that to happen, and we'll make sure that for our presentation next year that doesn't happen. And
Yeah,
thank you for your feedback. We'll make sure to work on it.
Yeah, thanks a lot, guys. Zoom, please leave now. The next team is waiting. Thank you. Hello, and I welcome you all to the finals of IRDC 2022. The next team which we have is Team Yuvon from IIT Guwahati. So before we move to the presentation, guys, let me remind you all the time limit. You have 16 minutes to speak, and then we will have Q&A for the next 15 minutes. So you can start when you're ready.
Greetings. We are Team Yuvon from Indian Institute of Technology, Guwahati. Our rover Yuvon is designed by a dedicated team of 40 members. The rover is divided into 4 primary subsystems, namely mechanical, manipulator, electronics and software, and the bioscience subsystems. Starting with the mechanical module, we have worked over designs which would provide traversal capabilities and stability to the rover. It comprises of chassis, differential, suspension, wheels, and caterpillars. A brief overview over the components. The differential connects the rockers to each other and the chassis and improves the body stability and force balance on the wheels. The chassis provides basic structure to the rover and houses all components of the rover. The wheels and caterpillar system acts as agents of traversing and produce the required grip. The suspension is responsible for maintaining stability during rover operations. Now, some of the problems we faced were, how do we work in the low temperatures of plenum austral? How do we keep ambient temperature inside the rover? What material do we select to get the required strength? How do we maintain the structure of our design owing to the range of temperature changes which could lead to contraction and expansion? How do we deal with corrosion since we are sending a rover in a vastly unexplored region? How do we properly distribute weight? How do we generate enough grip to traverse slippery conditions? The first 5 problems were resolved by selection of proper material and the last 2 by appropriate design of structure. The material chosen for most of the parts is grade 5 aerospace titanium alloy, a material composed of titanium, aluminium, and vanadium. We had 3 materials in mind: titanium alloy, structural steel, and aluminium and its alloys. Minimum service temperature of titanium is lower than the other 2, keeping in mind the lowest temperature recorded in the exploratory region is 130 Kelvin. Lower thermal conductivity of titanium helps in retaining inside heat better than other materials. However, it is not enough. For this purpose, heat pipes are used, which will be further discussed in the electronics module. Higher compressive strength of titanium provides the necessary strength, and comparatively low coefficient of thermal expansion ensures that comparatively better maintenance of the structure of rover. Titanium has comparatively lower modulus of elasticity, which is made up for in the design of tires. Corrosion tendency of titanium is less compared to other materials, and hence, for all these reasons, titanium is chosen as the material for our rover. Now, the structural aspects are divided into wheel design, suspension system, and caterpillar design. Coming to the wheel, the outer shell is made and the spikes are made up of titanium alloy, and the inner rim is a honeycomb structure with tapers inwards made up of nitinol. Apart from its strength, nitinol is chosen because it can undergo significant reversible strain of up to 10%. Hexagonal cell structures, which are known to be flexible in both axial and shear loadings, provide an even greater measure of load distribution to the system. Now, coming to the suspension, we had multiple options like rocker boogie, caterpillar, grasshopper, double lambda, but none of them were providing all requirements regarding the terrain. So we combined two of them to create the rocker system. We joined the caterpillar in the rocker of the suspension and made a custom design to reduce ground clearance. The caterpillar is aimed to increase surface of contact, which would increase grip and distribute the pressure better. An actuator is used with an aim to increase surface of contact during climbing or declining over an incline. Now, handing over to the manipulator module.
Presenting the manipulator module. The onboard robotic manipulator has 6 degrees of freedom. It consists of a base, rotatory actuators and links, and an end effector. Firstly, coming to the base is the core which holds and rotates the arm. The structure of base is made up of hollow rectangular columns made of aluminium, which helps in effective load and stress distribution by keeping the weight optimum. A 30:1 worm gear mechanism has been used to rotate the whole arm due to high loading, carrying, and torque transmission capabilities. The main shaft is held with the plates using radial ball bearings and is connected with the worm gear using Oldham coupling. Thrust bearing have been used wherever rotating axial loads are prominent. Rotatory actuators are made of customary planetary gearboxes and planetary gear DC motors. The gearboxes consist of 2 epicyclic planetary gear trains, each having a gear ratio of 4:1. There are 4 planetary gears connected to the sun gear that drives the outer ring. Both systems are connected by a sun gear carrier, thereby increasing the gear ratio to 16:1. The links are made up of carbon fiber rods to keep it lightweight while not compromising on strength. Links are connected to each other by the actuators and has a spherical workspace with a maximum radius of about 1.9 meters. Lastly, coming to the end effectors, it consists of a gripper having 3 degrees of freedom, rolls, pitch, and gripping actions. Bevel gear differential driven by 2 motors is used to give pitch and roll controls. A servo has been used for gripping actions. We devised an adaptive gripper which allowed the finger to wrap around any small objects being gripped. It has a hand span of approximately 8 centimeters. Lastly, the missions of our manipulator is to remove obstacles like stone, gravels, which might hinder the transversing of the rover, scrappy icy surfaces to make it rough, thus increasing the coefficient of friction to provide better traction, and finally to extend or retract itself to shift overall the center of mass of the rover by traveling on extreme slope, thereby providing better stability. Now, handing over to the electronics module.
The electronics module is divided into 3 main subsystems: navigation and control, power, and communication. Navigation and control subsystem includes the connections, hardware setup, and the software. 2D and depth cameras, motors, and their controllers, components of bioassembly, are connected to the main computer through a network of microcontrollers. Antennas are connected to the main computer and base station to help in exchange of data. We have used the Arduino Mega as our microcontrollers and Jetson Nano as our main computer. These are linked through ROS. There is a GUI running on the base station that shows live feed from the camera as well as other control parameters, which will be used by the operator. Power. One of the major challenges of the electronics module is to power the rover for the extensive duration of 20 hours, controlling the temperature of the rover and efficiently supplying power to the individual components of the rover. A single battery pack won't be able to power the rover. So we use batteries as a primary source of power, and when they discharge, they will be charged by a secondary source. 2 lithium iron phosphate battery packs are used so that when one is being charged, the other is powering the rover. For secondary sources of power, there are different methods that can be used like solar panels, but sunlight intensity at the poles would be marginally low. Large solar panels would be needed that will increase the cost and weight. Also, dust storms are frequent in Mars, so solar panels are not the best method. Another option is the radioactive thermoelectric generator. However, it generates the radioactive waste and requires expensive radioactive fuel like plutonium. In order to be regulated and isolated, it also needs a large, bulkier nuclear reactor. So we choose to use SATS, that is Stored Chemical Energy Power Subsystem. In this, combustion of a gas is done and the generated thermal energy is converted to electrical energy. The energy generated can be used to charge the batteries as well as keep the rover warm, enabling it to function even in cold weather. In this case, lithium nitride is the fuel which we are carrying, and we are using CO2 as an oxidant that we are extracting from the atmosphere.
Heat pipe channels are connected to the reaction chamber with proper insulation. These channels run throughout the body of the rover and regulate the temperature of the subsystems. To keep track of the rover's temperature, we have also placed temperature sensors at various levels. Our heat rejection system kicks in if there is an overheating situation and returns the rover's temperature to normal. The various components of our rover are connected via a power management board. This board has many buses that connect the battery to the various components of the rover subsystems. To provide the required voltage to different subsystems from the main source, VPTs, space DC-DC converters are used to supply required voltage from 24-volt battery. These are isolated, radiation-hardened converters and can be easily used to reject back EMF, noise, and electrical surges. With these converters, we can take input voltage of 24 volt and can provide various output voltage. And to meet our lower voltage requirements, we have used PPT point of load converters along with phase converters. At last, we have applied an EMI filter along with short circuit protection. Communication. The major requirements of the communication were that a wireless connection between rover and the base station is needed. This connection should work over a range. The drawbacks of using a 2.4 or 5 gigahertz radio waves is that for the range required, the antennas will be very bulky. These antennas, because of very high frequency, are not great at overcoming obstacles, and hence these antennas usually require line of sight. And the problem with the line of sight is it would require a 60-meter long tower at the base station to have a range of 20 kilometers, assuming that Mars's surface is a perfect sphere. This is not feasible. We overcome this problem by implementing skywave propagation. In this, the radio signals are reflected by the ionosphere, but to be reflected, the waves need to be less than a certain frequency. On Mars, this frequency is 4 megahertz. A few things about antennas. Transmitter antennas are usually big. Their size is proportional to the wavelength of the wave, and at low frequencies, the wavelengths get very big. In order to design a circular antenna of 4 megahertz or lower, the minimum diameter of the antenna will have to be 2.4 meters, which is again not feasible. So finally, we get to the mechanical antennas. These antennas use piezoelectric material. These can generate frequencies of up to a few hundred kilohertz. These are also compact in size. PZT material converts mechanical stress to electrical signals and vice versa. The frequency of such devices depend on the two major factors, type and the shape of PZT materials used in the antenna. Amplitude modulation method is used to encode a signal with the carrier wave, and the resulting signal is applied to the mechanical antenna. Moving on to Bioscience.
The Bioscience module undoubtedly holds the most significant role in the whole Martian expedition. A thorough process of collection, experimentation, and analysis is done on the body of the rover, presenting us with insights on Martian life and the planet itself. Mission with the examining of presence of hydrogen on the surface of Mars in form of water, the search for evidence of a habitable zone to support life forms, and the chemical and isotopic composition of the Martian atmosphere. The module aims to further planning and scientific research, inspiring hopes of life thriving on the red planet one day. Beginning with the first of two subparts, the drill assembly. Auger bits are used to drill the soil and ice. Once drilled, the sample is collected by claw-shaped collector and deposited to the testing assembly. Path to life detection. Path to life detection in Planum Australis for the rover begins with the analysis of environment, followed by the soil and subsurface analysis. Thus, a combination of all three will be instrumental in commenting on the habitability of the zone and the existence of life form. Foremost process carried by the rover is the environment analysis, TECP, or the thermal and electrical conductivity probe. The Martian soil thermal and electrical conductivity provides insight on its bulk porosity, composition, and grain size. The instrument is designed to emplace thermocouples into the Martian subsurface, thus determining the planetary heat and charge flow. UV radiation detector. High radiation levels represent an additional difficulty for the survival of life on the surface. UV radiation detector is employed to measure rays with absorption spectra in ultraviolet or visible range. The sensor linked to the screen will detect the desired wavelength and will eventually deliver readings based on the results acquired. Pyranometer. Life on Mars highly depends on the quantity of solar flux that falls on the surface. To measure the solar radiation flux density on a planar surface within a range, pyranometer is used, in which the thermoelectric detection principle is employed. Radioactive elements. The Martian surface is constantly exposed to high levels of cosmic radiation. Without any protective magnetic shield or thick atmosphere, radiation from space can reach the Martian surface almost unimpeded. The Geiger counter exploits the natural process of ionization to detect and measure ionizing radiation in Martian atmosphere. Once done, the rover moves on to the soil and subsurface analysis. The major components that Yuvon houses for the process are XRF spectrometer, TEGA, the thermal and evolved gas analyzer, neutron spectrometer, and GPR, the ground penetrating radar. Going in depth of each component, we have X-ray fluorescence spectroscopy, which is a non-destructible analytical technique used to determine the elemental composition of soil ice. It can detect almost 15 elements, namely potassium, calcium, etc. TEGA, or thermal evolved gas analyzer. It is composed of two separate components, the thermal oven, where the soil and ice sample is heated, and a mass spectrometer, EGA, the evolved gas analyzer. The major scientific objective of TEGA is to search for evidence of organic material, such as carbon-based compounds, oxygens, nitrogen, and is also useful in searching for traces of organic material that may potentially exist on the Martian surface. The neutron spectrometer, used for sensing the amount of hydrogen atom to detect presence of water. GPR, or ground penetrating radar. GPR uses pulses of electromagnetic radiation to image the subsurface. It captures images below the surface of the ground and detects variation in composition of the ground material. The core sensor used in the model includes thermal camera. When the camera is pointed at the surface having geyser eruption, it shows temperature difference at the point of leak caused by the pressure variance. Anemometer, used to measure wind speed and direction. It is mounted at the top of the assembly. The soil moisture sensor measures the volumetric water content in the soil using the properties of soil, such as electrical resistance and dielectric constant. The pH sensor, used to measure the pH of the soil. The microphone, used to record audio samples and detect geysers using sound waves. The BME 280 sensor, it reads barometric pressure, altitude, temperature, and humidity. And last, the USB microscope. It is used to detect the texture of soil ice sample. And that is the bioassembly of Yuvon. With this, I would like to conclude our presentation, and we are open to questions. Thank you.
Hello, I have a few questions. You used Caterpillar for the wheels, and what will happen if your Caterpillar fall off the wheels? Like, do you have some solution for that?
If the Caterpillar stop working, then we have taken enough measures that the rover will be moving. We can assume it like a four-wheel drive car. If a four-wheel drive car's first two wheels stop moving, then it can be actuated by the rear two wheels. So, for example, in this case, the rear four wheels will be still working, and hence we can drive as well as use differential drive to turn or rotate the rover.
Okay, and what will happen if the Caterpillar will be blocked with some debris or Martian rock and so on? Like, do you have some solution for a big friction that this Caterpillar will make then?
Okay, so for that, we have actually covered the Caterpillar wholly, so there won't be any chances of any contamination going inside the Caterpillar itself. So we can ensure that it won't be stopping to work, or it won't be resisting to revolve around itself.
Okay, so what will happen if the Caterpillar will stop, like the mechanism will fail, and you will still have friction without any debris and so on? What is the procedure after that?
For that, we have an actuator, linear actuator. So what we can do is we can just actuate the linear actuator above, so it lifts the Caterpillar completely above.
Okay, so another question. You used these hexagonal structure wheels, and what will happen if some Martian regolith or rock or debris will stuck in these free spaces of this hexagonal structure in these wheels? Like, do you have some procedure for that?
Actually, we have designed the hexagons such that they are tapering in shape. Like, for example, they are tapering outwards. So if there is some debris which gets into it while rotating it, while the wheel rotates, the debris will fall out even.
And how can you provide that the debris will like fall out of the structure? Like how it will happen?
If possibly there is some gravel or dust inside, then due to its tapering shape and due to gravity, it will fall out. But if there are some like boulders or something, then I guess it won't be able to do the same function.
Okay, thank you.
So I have a question.
Yeah, go ahead.
Okay, thanks. So it's about again science task, and I'm curious about what do you define as the habit? Like, so I have two questions. So first is, how do you define the habitability parameters? Like, what parameters are you expecting to see? And if you see them, you will consider that site habitable. Once you answer this, I'll ask my next question.
Okay, sir. So for the to explain the criteria of habitability, we follow the path of the rover. The rover follows the path with the first going with the environment analysis. May I have the slide? The rover starts with the environment analysis. First, it does is the UV radiation checks the UV radiation level, the thermal electrical conductivity, and the solar flux level. If these if the readings if the readings are within the required range or the net range of habitability, then the rover moves on to the soil analysis, where the rover takes soil samples, soil and ice samples, which are then further analyzed using TEGA and X-ray and XRF, the spectroscopy. And if the readings are checked according to the what are the data and what are the chemicals and present in it and the composition, if and accordingly these are then further assessed by the and if they are habitable and if they are within required range, they are then further the rover moves on to the subsurface analysis, which includes water and checking for the presence of hydrogen and composition of subsurface.
Sorry
And then
to interrupt.
along
So,
with
yeah, it's fine. I understood what you are doing. I'm asking about what values are you looking for? Okay, say not values. Say there is, okay, let's take an example. You have soil analysis, right? You are saying required elements or presence of required things. So what are the required elements you're looking for?
Okay, sir. If we go with the soil analysis, when it is used in a TEGA, we be doing the XRF, the spectroscopy, and it will be used to check the presence of any organism. If there is, if every organism releases a different fluorescent spectro, and that is then measured according to the XRF, and that creates a spectrography profile. Then further, the soil sample is heated in the TEGA, and the gases released are then analyzed. If they contain contain the amount of carbon, nitrogen, or oxygen, these then or ammonia, these are then sampled as to how much they are, and accordingly the data is created.
Okay,
And
the next.
Yes, sir.
Okay, yeah, the next question is, so you had like unlimited budget, right? So I'm curious to see like why have you used sensors that are like 500 or 600 rupees? Especially the science module, it has sensors like humidity sensor or like the microscope. So all that can be bought within 5,000 rupees, the entire suite of sensors that you have listed. So any particular reason for choosing such cheap sensors? Also, they are not very sensitive. Yeah.
So we worked on the our requirements and the features they provide. We were getting say for the BME 280 sensor, we had another option like BMP 280 sensor, but it does not provide us the data of humidity. Only BME provides that. So we went for the BME 280. Others are almost self-explanatory. So we needed for the thermal camera, imaging, we needed a thermal camera, and for the speed we had anemometer. Also, the calibration was stable in all these sensors.
Thank you.
Yeah. So guys, I noticed that all of your drive systems, right, they're pretty exposed. Like, so do you have any kind of contingency for cooling them? I mean, sorry, for keeping them at optimum working temperature and for dust, for example. like your linear actuator and all of those things, right? They seem to be pretty exposed. So what is the strategy for that?
So all the actuators and motors that are exposed to the environment are covered with insulation like aerogel or polyurethane. So
You're not audible.
Hello.
Yeah.
So all the actuators and the motors which are exposed to the environment are actually covered with an insulation, so as they not directly affect them. Like insulation like aerogel or polyurethane can be used to cover them.
Got it. And you guys also didn't talk too much about your navigation and your autonomy. So what is the strategy for the rover motion to testing site?
So actually the rover is controlled by the live feed that we are getting from the camera, and the images are transferred to the base station using communication. And the rover is actually controlled by the operator sitting on the base station, completely relying on the live feed. The
Got it.
odometry is done using the wheel encoders, IMUs. The data is fused. The data coming from them is fused. And also we have used a stereo camera. So the point cloud generated by the stereo camera can also be used to integrate with the other data so as to generate a more precise odometry.
And if you're anyway teleoperating, then what's the use of the odometry?
Sorry?
If you're anyway teleoperating, then what's the use of the odometry?
Yeah, to actually get where the rover is traveling and how much distance it has traveled. We should know that.
Yeah, so I think similar feedback for what you guys got for science, right? Like I think the hardware is severely under capable for what you guys want to achieve, right? Your Jetson Nano and your Arduino and all of that, fusing all of this is not really going to happen. So probably just keep that in mind for your hardware in general. Yeah.
Yeah, sir. Okay. But like we thought of using a much simpler system, not going for much sophisticated as like microcontrollers like Arduino Mega can do the job of providing the signal to the motor drivers and taking inputs from.
Yeah, so there are some real world challenges in that, which is the reason why they're not used industrially, right? There's a reason why your Arduino Mega doesn't run on a car, for example, right? And you're sending your rover remotely to Mars, which means there is some reason. So you guys need to dig deeper into those things, right? Why are those industrial suits not being ordered off Robo or Robo kits, and why are they being procured from somewhere, right? So yeah, just probably look into that for your next version of the rover. Yeah, will really improve your design a lot more.
Sure, thanks.
Yeah, I had one question. Yeah, can you go back to the drive system ones with the caterpillar and the wheels? Yeah, I want to know whether the wheels and the caterpillar are using the same motor or not.
Can you repeat the question, sir?
Whether the caterpillar system and the wheels, they are using the same motor or different motors?
Yeah, the caterpillar system, there are two sprockets in the caterpillar system. So one of them has the motor, which is same with the wheel. And the front
So
one is.
how do you make sure that the caterpillar system and the wheels are moving at the same RPM? Because if they are different RPM, then one of the systems is going to drag the another one. So how do you make sure that the the RPMs are synchronized?
Okay, so for that, the motor which is driving the caterpillar is also NDC encoder based motor. So what we are doing is we are taking encoder data from all these 6 motors and then driving it accordingly.
Okay, and why have you chosen DC motor? DC motors will be, in the long run, they are going to suffer, require more maintenance than, if you choose to use a BLDC motor. So suppose
Yeah,
your
we have
rover is going to Mars. Yeah.
Yeah, we have actually not like specified what type of DC motor it is. We have used DC planetary geared BLDC motor. So BLDC motors are brushless motors. So in that, the wear and tear is usually very less as compared to the normal brushed motors.
Okay, so you're using encoders to make sure that the RPMs are same.
Yeah.
Okay. Yeah. Thank you.
I have a follow-up question. Can you hear me right?
Yes, sir.
Okay. So on a design point of view, what was your take on shear strength problems for your caterpillars specifically? because that's not entirely clear for me. I mean, I know your mechanism might be beneficial for cases like, let's say, decreasing the risk of cracking the ice, like you mentioned on your report, but don't you think it might affect the risk of vibrations on your rover that might affect your components more than you anticipated? And if that will ever happen, how will you respond specifically? Like, can you give me more detailed answers that before?
It is not specifically used for cracking the ice surface. It is just used to provide a better traction over the surface. Like we have threads and we have a lot of surface area. So that will in general increase the traction. And from the shear stress point of view, we haven't thought about it really.
Okay. Thank you.
Yeah, I have a question. So as you are searching an area for habitability, so like how do you zero in to an area? Like you're going to do the experiment on this area or the other area. So what is the strategy you are using there? Or what's the plan?
So for the plan, first of all, for the general plan for why we are in the Planum Australe, so it is a region for the with the lakes, various lakes, based on the various studies and reports done earlier. It is an area of lakes and soil, ice covered. That is why it is has according to the report, a very stable water body under it. From the reports done by various various other missions. The space also the data collected from spacecraft and micro the average mass, the average temperature of the area remains constant. So that is why we have narrowed down to why we are using it, doing the experiments on the Planum Australe. Further, to narrow down the area in there, we are doing.
I'm asking like that area has been given to you as a huge area. So you have a lake, you have a regolith, and then you have an ice. So which area you first go to? How do you select that? Like, do you have any strategy or plan for that, or whatever area you get, landing to, you just start exploring it?
So as we are near the soil and ice boundary, we start with the taking the sample from the soil and sample of the soil and ice. Further, we do the environment analysis. If the area is the analysis of the radiations and the solar energy is within range, then there are chances of a stable atmosphere. So we further move on to the soil analysis in that area. If that is unfavorable, we move on to the next area, and then we work on again to the environment analysis, which if again is favorable, we do the soil analysis there, and then further we do the subsurface analysis.
So what do you call favorable in that? Like what all parameters you are looking into?
So for the environment analysis, we already have the ranges, stable ranges. If we compare it to the atmosphere and the Earth, we have a stable ranges for the UV radiation levels and the solar density. If they are within that range or nearer to it, we consider it a favorable area condition. Then we move on to the soil analysis.
So only the chemical analysis or these biological analysis result into favorable and non-favorable conditions. So you're not focusing on any of the physical features. Texture of the surface or some craters, some deep areas, something like that.
Yes, sir. We are working on. We are taking that in care first, but we need to narrow it down. So once we are done with the environment, then we go on to the soil analysis, where the texture is taken care of, and what is the composition of the soil and the atmosphere, along with the pH. As we are already as you can see, we are using the pH sensor. So the pH of the area is also taken care of, and further once we are done with the soil analysis, which includes all the remaining data, sir.
Okay, thank you. I think we don't have any further question. So thank you very much, guys. And it was a pretty good presentation. I think it's far more, better than the report you submitted. I really like the PPT which you have shown. And you have timed it well. You have taken the complete time, and you have been able to explain the system in a better manner. So yeah, thanks a lot. And now you may leave. So yeah, the second day is over now. We still have 5 teams to go. So that will be tomorrow. And yeah, tomorrow is going to be a hectic day. It took 2 hours 10 minutes today, and tomorrow it will take at least 30 minutes more than this. And today we had 2 new teams, IIT Roorkee and IIT Guwahati, and 2 teams which participated earlier. The teams which are participating tomorrow, we have 2 new teams and 3 teams which participated earlier as well. And the current champion and the current runner-up both are scheduled to be there for tomorrow. So tomorrow is going to be exciting.